Hey folks, welcome to another fun-filled episode of Working with Rational Expressions. So we're going to delve into a class example on page 151, and we're going to use it to look at the intricacies of dealing with common denominators. Working with radical expressions is going to be no different than if you were working with straight-up fractions. Before you can add or subtract them, you have to find a common denominator for each term, and it's quite often beneficial and more efficient if you're able to find a lowest common denominator. It'll save you the simplification and dividing through at the end, which when we're dealing with more complicated higher order expressions will be nigh near impossible in some cases. So let's take a look at this question on page 151. There is no doubt that you could come up with a common denominator by multiplying each of those denominator terms by each other. You can go a minus 3 times a squared minus 9 times a squared minus 2a minus 3, and you are going to get a common denominator on the bottom. No doubt about it. The problem is that you're going to get some really, really messy expressions. Think about just the a term. If I multiply a times a squared, all of a sudden I'm dealing with an a to the power of 3, a cubic term. And then if I multiply that a cubed term by a squared, now I've got an a to the power of 5. Good luck trying to factor something with a to the 5th plus or minus a to the 4th plus or minus a to the 3rd plus or minus a squared plus or minus a variable or a constant. Good luck. It would be impossible for most mortals, I guess. So instead, we're going to start looking into little time-saving tricks that will allow you to choose a good value for a denominator and then work through the problem with that and show you how easy it is sometimes to do the simplification at the end. The first step that we're going to do is try to simplify any of these denominators we can so that we can see what we have. And then sometimes new paths open themselves up to us and we can see things that we can't see right now through the clutter and the fog. So do you notice something special about the a squared minus 9? Well, you should. You should pretty much immediately identify that as a difference of squares or a difference of perfect squares, which can be what? A minus 3 times a plus 3. And you should begin to be familiar and comfortable and fairly efficient in identifying a squared minus 2a minus 3 as also being integrally factorable. That is, factorable into integers. So what is that going to look like? Well, the first term is unchanged. There's nothing we can do with that. A squared minus 9 becomes a plus 3 times a minus 3. And you can just verify that works, right? A times a is the a squared. 3 times, or negative 3 times a, so negative 3a plus 3a will eliminate any a to the power of 1 terms, and then plus 3 times negative, so gives you your negative 9. So we are good to go over there. And you get more comfortable dealing with simple trinomials like this and identifying that they are integrally factorable. That is to say that the factors are integers. So negative 3 and plus 1. And if you want to verify, you just multiply these out, expand them, right? There's your a squared term. Plus 1a minus 3a will be minus 2a, and then negative 3 times plus 1, negative 3. Boom, there you go. Think of these as being your high school times tables. Being able to factor trinomials with or without a coefficient in front of the a squared term will become a little bit more automatic, just like your times tables and your multiplication facts are now automatic. You'll be able to, the more you work with these, be able to do these by inspection. So what's the next step? Well, at this point, what you want to do is identify what you're working with. Because as I said, you can multiply all of these terms by each other and get a common denominator, but I think we can figure out that we don't have to multiply the a minus 3 denominator by everything here because this is a little bit redundant. So first identify what your lowest common denominator is. It's going to be a plus 3 times a minus 3 times a plus 1. So I think you'll see that in the first term, to bump it up to a common denominator of all of this, we have to multiply the top and bottom by at least two parts, an a plus 3 bit and an a plus 1 bit. Reinforce the idea that we're not changing the value of any of the terms and therefore of the entire expression. What we're doing is multiplying it by 1, right? A plus 3 divided by a plus 3, that resolves as a 1. We're multiplying it by a fancy way of saying 1. And the reason we're doing that is so that we can add an a plus 3 term into the denominator of that first expression. So there's the top and bottom of the first term of the expression multiplied by a plus 3. Remember that we're still looking for that common denominator. We're going to need to throw in an a plus 1. So we're going to multiply top and bottom now by a plus 1. And boom, we got it. So the first term of this rather complicated expression is all converted into that common denominator, that LCD that we're looking for. And now we'll do the same thing with the second two terms. We're going to multiply the middle term by a plus 1, which is a plus 1 over a plus 1, right, to make sure that we're not changing its value. And we're going to multiply the second term by a plus 3 over a plus 3, right? So what do we see? Well, here's the a plus 1 term in the middle, okay? A plus 1 divided by a plus 1 is 1, so we're bumping it up. The first two terms now are dealt with. Let's do the second term, sorry, the final term of the expression. And now we've got every term of the expression with a common denominator of a minus 3 times a plus 3 times a plus 1. So the next step now will be, well, if we've got a common denominator, then we can simply start adding and subtracting all of the terms of the numerator and bringing it over a single fraction line. So let's do that. All right. So all we've done is added the numerator of the first two terms and then subtracted the last numerator. Take a look. It looks exactly like that, yeah? Good. Let's tidy this up a little bit. Let's get rid of the 1 coefficient because 1 times all this is just 1. Same thing in here. So let's tidy this up a little bit. Yep, that looks good. And now we can do a couple of steps here. We've got some like terms here. We could do a binomial expansion in the numerator and make it a little bit more cohesive. So let's do that. All right. And then finally, let's gather up the like terms. Looks like the a minus a will eliminate that. So we should have a 4a term. Yep. All right. So take a look at the steps we've done. We've just done some simplifying and tidying up as we're moving down. And we're left with finally a squared plus 4a plus 1 all over that common denominator of a minus 3 plus a plus 3 plus or times a plus 1. And so what we've got here now is a nice, tidy, simplified expression of a squared plus 4a plus 1 on the top, divided by our common denominator that we are looking for of a minus 3 times a plus 3 times a plus 1 on the bottom. It would be nice, and you should always look to see if that top quadratic up here can be further simplified. Can that be factorable into integral factors? I don't see any. But beware, because you may not be finished here. In this case, we are, but if I was able to convert this, if this was a quadratic with really nice, cool integral factors, then maybe I could do some more dividing out. But this looks to be the extent of what we can do. So the last thing we're going to do is look at non-permitted values for a, that is, restrictions on the value of a that would, if we did allow them, make the whole expression blow up. In the first term here, if a were equal to positive 3, 3 minus 3 would be 0. 0 times anything would be 0. This fraction would have a 0 in the denominator, and the expression would become indeterminate or undefined, and so that would not be allowed. Likewise, if a were equal to negative 3, the whole denominator would equal to 0. And finally, if a were equal to negative 1, then this whole denominator would equal to 0. So there are 3 restrictions, it looks like, 3 non-permitted values for the value of a. A may not equal to plus or minus 3, and a may not equal to negative 1. If this confuses you, go back to some of the videos I posted in terms of what non-permissible values are and why they are non-permitted. There's 2 situations where you're really curious and very interested in them. One is with variables in a denominator of a rational. And finally, when the variable is inside of a radical sign, that is when you have a variable as a radicand, because then you can't have the square root of a negative number. Here, we're only considering denominators because that's all we have. Here is your final simplified version of this question, and you are good to go. Peace out. Math on.